Okay, great. So welcome everyone for our second day. I'm very excited to introduce the second day kind of keynote speaker. So we have Tina Eliassi-Rad, and we're very pleased she's going to talk about hypergraph.
Great. Thank you very much. And thank you for the organizers for inviting me, and thank you all for being here. So what I originally wanted to talk to you about was a tale of four papers that are presented in this hypergraph. But then I was asked to give two talks. So what I'm going to do is I'm going to talk about the first two papers today and talk about the other two papers on August 12th upon my return. And by then I may have two other papers on hypergraphs in preprint, so I may foreshadow those at that time. So since yesterday there was a discussion about visualization, this visualization is by Mathematica. I don't get anything from Wolfram for pitching Mathematica. I will also have a QR code at the end of my talk where you can download the slides. But this I created really quickly, and I think looks fairly nice. And the reason Wolfram got excited about hypergraphs is because he believes that you can represent all the physical world with Mathematica. And, you know, we can have a drink and talk about him. But because he's so, he likes hypergraphs so much, and he started this in 2020, if you are a fan of Mathematica, there are a lot of tools that you can use above and beyond just visualization. All right. So the first paper came out in SciAm Review. You may have seen it. It was with my student Leo Torres, who did a postdoc with Jorgen, and Sizemore Belvins, who's a student of Danny Bassett, and Danny Bassett at University of Pennsylvania. And so the idea was to think about what is a prototypical analysis pipeline for complex networks. And we came up with this, where you have a system and you want to look at what dependencies exist in that system. And then based on that, you pick a data representation, and then you formalize the system the best you can, and then you try to interpret the results. And here we were talking with, I was talking with Michael yesterday. I feel like already there are factions in terms of like, what is the best way of represent higher order systems. I am not here to praise one versus the other. I have no dog in the fight. You guys can fight it out. I'm a computer scientist. I just care about prediction accuracy, supposedly. So machine learning, where does machine learning systems usually come up? The machine learning systems usually come at this point, and machine learning people typically don't pay that much attention to the processes that created the data or the system itself, to their own peril, I must say. And so let's talk a little bit about these dependencies that you want to capture. One of them, for example, would be subset dependency, right? So if the blue, red, and the green author wrote a paper together, then each pair of them is also a co-author. Maybe you care about temporal dependencies in your system. Maybe you're trying to model the brain and you care about the spatial dependency. And of course, you can have more than one of these dependencies. You don't have to have one of them. We all are familiar with subset dependency, and you may think, oh, it's ubiquitous everywhere. Like, for example, here, while these two squares have different colors, they're still squares. But it is not the case. There are certain systems where when you look at your nodes and you look at your relationships, here nodes are molecules, you do not have the subset dependency. And so why would you add all the machinery for subset dependency if subset dependency does not exist in your system, right? You will make your life a lot easier by using a simpler representation. And then in terms of the temporal dependency, if I give you, for example, a list of passenger commutes, and I tell you to infer the subway map of a city, you really need to have some temporal dependency captured in whatever you're representing. Otherwise, you won't get the exchanges correctly, right? And I don't care like how powerful your ML is, et cetera, right? You guys know this. You will need to know that. Otherwise, you won't be able to get the exchanges well. And then there's, as I said, spatial dependency. This comes a lot in terms of analysis of the brain network, where regions that are close to each other fire together. And so you want to capture that at the same time. Now, there are, of course, other sources of dependency. I did a lot of work on however big your data is, it's not complete. Again, like network scientists, complex systems folks pay attention to this, but computer scientists often don't. And so one way that you can formalize it is as an optimization problem of if you have a certain budget, what kind of questions should you ask so that you would see more of the system and do better on your task. This is, if it's a learning task, it's called active learning. If you're just exploring, then it's called active exploration. The other one is data acquisition and processing. So whenever you're working on a co-authorship network, you're introducing a lot of triangles. And maybe those triangles are exactly what you want. But for certain tasks, for example, we have this project on how much signal is there in co-authorships in terms of who gets a tenure track position in America, which is an advantageous position. And actually what we've found is that if you, for example, model it in terms of simplicial complexes, where you do have the subset dependency, it's too much. The system gets overwhelmed. What actually helps is a hypergraph where the exclusivity comes about, right? So if like Tina publishes with Jorgen, Joost, and Barabashi, there's that exclusivity that comes of being in that set. You don't need that pairwise altogether. And then, of course, there's the research question. And at this point, I feel like I'm preaching to the choir because you're all really good scientists and not bad engineers. And so now we talked a little bit about the dependencies. So then you think about, okay, well, how would I represent it? And so three of the most popular ones are graphs and simplicial complexes and hypergraphs. And of course, with graphs, as you all know, we're interested in cliques, we're interested in paths. With simplicial complexes, you're talking about topology. So you're looking for holes and cavities. You're looking at maximal simplices where no other bigger simplices includes it. For hypergraphs, of course, you're interested in, for example, structures that are absent. So dyadic structures, for example, in this case. So based on how you present it, again, you kind of get different views of your system, obviously, right? So if I'm interested in this green node and I represent it as a graph, I'm like, okay, I have 4 direct neighbors and 2 triangles. If I represent it as a simplicial complex, I'm like, okay, I have 4 direct neighbors and 2 simplices, 2 simplex. And if I represent it as a hypergraph, I'm like, okay, I have 2 dyadic neighbors and 2 neighbors from a larger hyperedge. And you may say, why should I care about this? Well, the reason you should care about this is that, again, the results that you get and what you publish or what you take to your manager will be different, right? So if you represent it as a graph, perhaps you would find this core periphery structure. If you represent it as a simplicial complex, you'll find these big cavities. And if you present it as hypergraphs, perhaps you'll find that there are different communities, and these communities are not the core periphery community. And so we did this small experiment that's in the paper, and all the credit here goes to my student Leo and Anne, the students who were doing the work. So you start with a paper author network. Obviously, if you do a projection of this bipartite network, you are going to get a co-authorship network. And so then you're looking at pairwise interactions. With simplicial complexes, you're looking at sets of authors that have worked together. And as I already mentioned with hypergraphs, there's this notion of exclusivity when you are presenting a paper as the authors as the hyperedge. So the paper is the hyperedge and the authors are the nodes. And so we looked at, this is computer science papers from DBLP, a service from Germany. And so what you can do is you can just see, okay, what are the correlations? So this is publications in 2016. And you can do this, okay, well, what is the graph degree for a node and what is the hypergraph degree for that same node, right? What is the simplicial complex degree? What is the hypergraph degree, et cetera, et cetera. And then you can do like a Pearson correlation. And as you would expect, the frameworks that allow you to capture polyadic relations, so more than 2 relations, they tend to be more correlated with each other than the polyadic versus the graph degree. The other one that we looked at, these are emails and participants. On the x-axis, you're seeing the average node clustering. So around a node, how many triangles there are, or how many possible triangles it could have, and then you average over all the nodes. And on the y-axis, we have the average node clustering in the hypergraph. Now, one of the things is that there are many different ways of representing what is node clustering in a hypergraph, right? And so if somebody comes and says it's my representation versus somebody else's, you need to say why. Like, why do they have this kind of dictatorial tendency that it has to be theirs? But basically what you're trying to capture is a similar notion of what you're trying to capture with node clustering, which is some normalized extra overlap that exists between two hyper edges. So the higher you are, the neighbors that connect the hyper edges do not contain the particular node. And so here, what we're trying to just show you is that, again, depending on how the framework that you use, it's not like they're going to be correlated. It's not like the clustering coefficient, which is a very important measure on graphs and hypergraphs, et cetera. They are not correlated with each other. The other thing that we measured was how many hyper edges are within a bigger hyper edge, right? And so here, the higher up you are, you have more intra-team communications. So there are more emails between the participants in the team. And again, this is the color you see, and we saw no obvious patterns there that could be used. A lot of people have done work on what's called network neuroscience, right? Representing the network, the brain as a network. And it's similar ways of thinking about it. So if it's a graph, you have no subset dependency, you're looking at pairwise. If it's a simplicial complex, then you're looking at co-firing, you have the subset dependency. And if it's a hypergraph, you're looking at exclusivity. And so here, Danny Bassett at Penn, who is a student of Ed Ballmore at Cambridge, has done a lot of nice work. And so depending on what representations you pick, you can find different things, right? Again, I feel like I'm preaching to the choir here. If you want me to go slower, I can go slower. And in fall of 2023, with Genestra and others, we went to the Kavli Foundation in LA, and with network scientists and neuroscientists, and we have this position paper in Journal of Neuroscience in terms of why neuroscience needs network science. So one of the things would be, can network science help neuroscience to help patients that have mental diseases, for example, or any other kind of dementia. Now, of course, there's lots of different variations. There's directed, there's weighted, there's dynamic. Dynamic is interesting because computer scientists, one of them, we ask you, do you want it fast or do you want it good? And you want it fast, so I'm going to discretize it, right? And oftentimes they don't pay attention, my people don't pay attention to the dynamics, to the pace of the system, right? Which obviously you have to pay attention to when you're looking at dynamic networks. There's multiplex networks, there's multi-layer networks. There's a nice figure there from another paper about what the differences are. There's other higher order networks. So Ingo Schultes in Germany, for example, has done really good work in terms of like having some memory, where like whenever you get an email from me, that email first came from Jorgen, right? And so you want to be able to capture that kind of a higher order. Then there's obviously all the multi-partite, bipartite, tripartite, et cetera. And of course, there's also this kind of motif-based networks where like the node itself, for example, is a triangle or a triad. And again, I don't have a dog in any of these, so you guys can fight it out in terms of which is the best representation. I don't think there is one big good representation. You just have to see what problem you're trying to solve. But there's some nice important problems to consider. So after you create, for example, a simplicial complex from your data, how do you interpret clustering coefficient? So how do you interpret triangles that are not shaded versus triangles that are shaded? The triangles that are shaded are saying that there is a subset dependency. How do you deal with communities? For those who don't come from network science, communities is basically that the density of edges within that set of nodes is more than what you would expect, or more than it would cross the boundary of that community. depending on what objective function you use. And again, here, how do you define the communities from a simplicial complex where you have the subset dependency versus a hypergraph where you don't? How do you measure diameter of a network when you have a hypergraph where it's not uniform, where every hyperedge doesn't have like 3 nodes in it? Can we kind of intertwine these different representations to be able to learn something? Or maybe you could like take out the subset dependency and do like an ablation study to see how much the subset dependency is actually helping you with the question that you're trying to answer. And on that note, I want to talk about homophily. Homophily is birds of a feather flock together, right? So on and so forth. And I'm going to highlight these 3 papers. They are not my papers, but I think this is an area that a lot of work can be done, especially since it has projections to machine learning and data mining. So the first one is Park and Barabashi. I'm not pitching it because Barabashi is my colleague. I genuinely like that paper. I liked it even before I was his colleague. And then the other 2 are recent papers that came out. One from John Kleinberg and Austin Benson, and Nate Veldette, who was their student, who's now at Texas A&M. And the other is by Ali Jadbabai and his students at MIT. And this just recently came out. So let's talk about homophily and why it matters in machine learning on graphs. So whenever you're doing node classification, you have a network, I don't care how you've represented it, you are saying that there's some kind of relational dependency. That is the probability of Tina being bad and Jorgen being bad, given that they have a link together, is more than the prior probability of both of them being bad. Think about guilt by association, right? Now, of course, if your network is, or your graph is randomly connected, then the best you can do, I don't care what kind of machine learning system you have and how powerful it is and how many parameters it has, the best you can do is you learn that the connections are random, right? And in fact, it may hurt your node classification. And a lot of the hype around graph neural networks, when you look at it, is because they have a lot of features. And so Austin Benson actually at Cornell had this really nice model where you're like, okay, I have all of these nodes. How many of you know about Pinterest? Or think Facebook, whatever, right? There are accounts. Those accounts have a lot of information. And let's say I want to predict whether I should like push you a shawl, right? And what he did was he learned a multi-layer perceptron. So treat all the nodes as IID, learn a multi-layer perceptron. Then what you're going to do is you're going to do label propagation. And by doing this, you have a lot less parameters, like an order of magnitude, less parameters. And he was beating some of the GNN models. And he was on the top of the leaderboard for a while with his small model. So it's really what they're using is all those features that comes about and not necessarily this link structure, because there's a lot of noise in that link structure and they do not get rid of that noise. So then with link prediction is the reverse, right? So I want to predict whether Tina is going to have a link to Jorgen and condition on the fact that they both like Apple products, right? I'm going to say that that link is more likely to appear than the prior probability of it, right? And so this is why homophily matters, right? Because you would like to have birds of a feather be friends, right? Instead of not being friends. Now you could try to learn what kind of homophily structure you have, but if you do have it, then you should use it and save the planet and not learn a model that has 100 billion parameters. So this is the Park and Barabashi paper. So what you have is, how many of you have seen this paper or remember? One of you, excellent. So you have capital N number of nodes, capital M number of edges. The average probability that 2 nodes are connected are M over the possible number of edges you can have, N choose 2. I'm just following their notation in the paper. Number of black nodes is N1 sub 1. Number of white nodes is N sub 0. Then you count how many edges you have that connect a black node to a black node, how many do you have that connects a white node to a white node, and how many do you have that connects a black node to a white node. And then what they do is they define two measures. One is dyadicity, which is what is the number of, so this is diageticity with respect to black nodes. What is the number of edges that connected to black nodes over it, what if the connections were random, right? This is very common in network science where you compare to what is random. In computer science, it's rare that people compare to what is random. It's just like, look at my accuracy, right? And then you get a lot of money. And then with heterophilicity, it's, well, how many edges do I have between a black node and a non-black node? And then what would be if it was random? And the thing with this is that if the labels and the connections are random, then you have a diageticity of 1 and heterophilicity of 1. And so then you can look at this space of where your network is, which is very nice. So this is easy and simple to understand. Then there are the folks from Cornell that came in and looked at simplicial complex or hypergraphs. And they said, okay, suppose I have C classes, so red, green, blue, and then I can count the number of red nodes I have, the number of blue nodes, the number of green nodes. Obviously, the sum of them would be the number of nodes that I have. Then what I'm going to do is I'm going to come up, it's just counting the affinity on this hypergraph of a fixed group of size k. So basically, if I look at all of the hyper edges that I have in my graph that have 3 nodes in them, how many of them have all of their colors be the same, right? So how many hyper edges do I have that have 3 vertices and they're all red, right? How many hyper edges do I have that have 3 vertices and they're all blue? It's kind of like that. And then, or you can say just how many it is that they're all red, they're all blue, right? So it's more like an addition. And then you have this baseline in terms of what if the connections were random. So the bottom here, the denominator is the baseline, right? If the connections were random. So, and then what they do, so as you probably know, John Kleinberg is very good with impossibility results. And so one of the things that they were looking at was for a particular class, what you want to know is what is the highest order in which you're going to have this kind of monotonicity, which is this ratio of affinity over baseline. As k increases, that ratio increases. So this ratio for k would be bigger than this ratio for k minus 1, right? And the k minus 1 would be bigger than k minus 2, and so on and so forth. And then they also define this other measure, which doesn't look at the ratio, but only looks at affinity score versus the baseline, right? And so I want the affinity score, the relationship between affinity score and baseline is affinity score being bigger than the baseline at k, and that relationship to hold also at k minus 1, k minus 2, so on and so forth. And then they prove this impossibility results that you cannot have like strict monotonicity when it comes to homophily, which you probably already guessed, and you cannot have a strict majority. And again, majority is just looking at the difference between the affinity score and the baseline being just random connections, what you would see in terms of random, a random system. And then the monotonicity is about the ratio. But what they showed in terms of the empirical results was that in many of the group settings that they have, what you're going to see is this kind of bowl-shaped ratio score. So here, this is in the US, Republicans and Democrats, is co-authorship. And on the x-axis is the number of people on the bill. So a bill here is a hyperedge, right? And then people who are on it are the nodes in that. And then this is the affinity score. And then this is the affinity divided by baseline. And basically what they showed is that across many different systems that they looked at, mostly social and information and marketing, right? Not brain, not biology, et cetera. What you're going to get is you're going to get this kind of a U-shaped figure that you're seeing. And the U in terms of the homophily going up happens when you're looking at that K, the number of people who belong to a certain group have the majority instead of uniform, right? It's not like it's 50% Democrats and 50% Republican. And that's what it says, right? So a large enough majority of group members are from the same class. So, all right, seems reasonable. What happened was the following year, these guys came along. And I'm going to start talking about the data they talked about, but they found a flaw in Kleinberg's paper. And this is, again, a point of discussion. And I think something that this audience is a good audience to ask. There are two questions that will come up. So they looked at, again, co-authorship relations. So they were interested in simplicial competencies. They looked at contact networks. They looked at co-sponsorship of bills. They looked at email networks. This is when a person goes in and is using multiple drugs, so hospital network, social relations, and this is like clicks on hotels, etc. So this simplicial complex is multiple hotels are browsed by the same user on this website. And so then what they did was they have all of these different statistics for them, like how many nodes you have, how many classes you have, what are the number of edges, what are the number of triangles, what are the number of tetrahedra, how many groups of size 5 you have, how many timestamps you have. They also looked at groups of size 6, 7, and 8. So these are simplicial complices that don't just have like 3 nodes in them, they go up. And like some of them, for example, this is a social network, you have plenty of groups of size 8. So what was their beef with the Kleinberg paper? What they showed with the Kleinberg paper was that the edge homophily that you get if you just have a graph is highly correlated with the edge homophily that you get based on their hypergraph homophily. And they're like, it shouldn't be like that, right? They were like, why is it that I have this high correlation? And because I have this high amount of correlation, because remember, I showed you, for example, with node clustering, there was no correlation between the graph representation and the hypergraph representation. And they're saying, well, what's going on? And what they're saying is that the hypergraph homophily that Kleinberg, Velt, Austin, and Kleinberg proposed isn't doing the right job, is not measuring homophily in a higher order because it's highly correlated with if I just had a graph. And so what they came up with was just changing the baseline, right? So the affinity is still the same. So here, for example, the triad affinity is I have 3 shaded triangles, but 2 of them have are composed of nodes who have the same color, right? This is all blue, this is all red, and this has a blue, so this doesn't count. So it's 2/3, right? And then the hypergraph baseline is the one that Kleinberg et al. I should just Velt. Austin, Kleinberg. It's bad to always just say the one who's very popular and everybody knows. So anyway, and so for them, what it was, okay, well, I have 2 nodes, 2 colors. I have 4 red nodes. How many structures of size 3 can I make out of it? So it's 4 out of 3. So 4 choose 3 times 8 choose 3 because I have 8 nodes plus the other one, the blue one, right? And so if you do this, you're going to get 1/7. And then what they did with their simplicial complex was like, no, the baseline shouldn't be what is random. The baseline should be the affinity score that you have at like k-1 skeleton. So here, if k was 2, so 2 simplex, I'm going to go to the 1 simplex, the simple, they call it 1 skeleton. And so the baseline would be how many triangles do I have and how many of those triangles actually have all of their colors be the same. So here you have 4 triangles that have nodes whose colors are all the same divided by 6 triangles, right? So then you just divide the triad affinity by the hypergraph baseline to get the hypergraph homophily score, and then by their simplicial baseline to get the simplicial homophily score. And if you're interested, if like what would it be if I just represented as a graph and use the dyadicity that Park and Barbashi talked about, then you get 5/3 for blue and red. And if you put them all together and say same color, you get 10/14. So again, their objection to Kleinberg was that the homophily on the dyadic level is highly correlated with the homophily in the hypergraph that they produced. And now they're like, look, there's no correlation. We won, right? Across the different data, et cetera. And so what they're doing is, okay, well, what was the homophily score, the edge homophily score versus when I went up one versus like when I looked at the simplicial complex score of size 3 and then versus 4, 4 versus 5, and 5 versus 6, right? So that's what they're selling. And then one of the results that they showed, which was interesting, here, so this is the group size. This is the homophily score that they have proposed. These are two different data sets. This was the clicks, and that was the hospital. And the red is the simplicial complex homophily score that they have, and the blue is a hypergraph homophily score. And what they're saying is, look, you can start at group size 2 and have a positive homophily, but with our measure, then at size 3, you're going to have no homophily. And then 4 and 5, you're not going to have any homophily, right? And then on the other one, you can even flip from minus to plus to minus. So you may say, why should I care? Again, the reason you should care is because machine learning heavily relies on homophily. And if you have this kind of system that goes up and down and the homophily changes with respect to the higher order values, then maybe we should think about what should be the relationship between homophily values on graphs, hypergraphs, and simplicial complexes, right? Because the Judd-Babai paper that just came out in PNAS is saying they shouldn't be correlated. That, like, for example, the homophily you get based on just dyadic representation should not be highly correlated with the higher order representation. And then the other question is, well, what should the relationships be when you go from a K order to a K plus 1 order? Should it be monotonic? We know that there are some impossibility results that the Veldet, Austin, and Kleinberg paper showed. But these are things that, you know, in part interest me into like which way should we go? Maybe there's no good answer. Questions? I can pause it. Yeah. Ideas? Maybe we, yeah, go ahead.
What if you try to formulate it in information theoretic terms? If you look at the probabilities of higher order dependencies that are not coming from lower order dependencies.
I love that. So that I don't know anybody that has done that. I think you and your lab should do that. Submit it to PNAS. I don't know of anyone within computer science that has done it. And so, but that's a great idea. I like that much better than what has been proposed so far. And as I said, there are implications for machine learning with respect to the answers to come with these questions. So then I know I have like 10 minutes. I'm going to go through the second paper that is under review at ACM Computing Surveys right now. And I felt like this is a good survey paper to present to you because my colleague Dima Kiryakov, who is a graph theorist, mathematician, philosopher, physicist, and philosopher at times, really likes this paper. So I'm like, okay, we won. We got somebody on that side to like our paper. So this is with these amazing people, Li, Bu, and Shen at KAIST. Shen is a professor there. And so you have a bunch of authors, you have a bunch of publications, yada, yada, yada. So what is the overview of the survey? We talk about data, then we talk about tools and measures, structural patterns, generators, and applications. And so the way that we're seeing this is that you have, for example, one paper, then another paper comes, then another paper comes. And so this is how your hypergraphs is being formed. And so we have, and I don't expect you to look at all of this, but we, the kids, the students did a really good job at breaking it up into, for example, you have the co-authorship domain, you have the Q&A domain, you have co-purchasing, review, drug, congress, social contacts, user behavior, biology, and recipe. We have links to where you can download these papers. What are the nodes? What are the hyper edges? how many vertices do they have, how many hyper edges do you have, and that could be also duplicates, and then number, by duplicates I mean the same people co-author another paper together, right? And then number of unique hyper edges. And then we have the tools and measures, and of course this is not exhaustive, so don't shoot me if your method isn't listed here. It is what it is. And so we highlighted 3 null models. So one is that you want to preserve the distribution of node degree and the distribution of the hyper edge sizes. This is the plain old configuration model. You have the random filling model where you would like to preserve the hyper edge size distribution, but not the node degree distribution. And then there's this hyper CL, so hyper Chang-Lu, where you're trying to preserve some notion of preferential attachment. So the hyper edge sizes are exactly preserved, and the expected degree of a node is approximately B of I. So when a hyper edge comes in, it tries to attach to a hyper edge that is already rich. Then we looked at different ways that people take a hypergraph and represent it. So you can have like a clique expansion where a hyper edge now becomes a clique, or you can represent it as a bipartite network, or what's called here star expansion. And then you can extract many different kinds of motifs from what you have. For example, based on hyper edges E1, E2, and E3, you can infer that you have a triangle based on this hyper edge. You would see, oh, I have a 3, 5, and 8 hyper edge as well, and so on and so forth. And these often are useful in, as I understand it, in like biological applications where they use a lot of motifs. And then there was a paper that was published again by Kleinberg's lab. And this is John Kleinberg, not Bobby Kleinberg. They're both at Cornell. They're brothers. With Comrie, where they looked at, well, what is an egonet, right? So egonet in a social network is I am the ego, and it's the one-hop induced subgraph, right? So my neighbors are my alter. On my alters, and then it's the connection I have to them and the connections they have to each other. And so you could go from what they're calling just a star, which consists of hyper edges that contain the ego node, and then you can go to radial, which is you have the star and then you add the hyper edges consisting of the alter nodes, and then you can also add hyper edges containing not only the alter nodes as well as other alter nodes. So more structure that you can capture. Why are these interesting? So if you can reduce your hypergraph to a series of a series of egos, hyper egos, then you can learn on those hyper egos instead of the hypergraph itself. For example, you can parallelize, etc. And then obviously, like similar to the K-core decomposition, you can also decompose your hypergraph where you're looking at it at like K equal 1, K equal 2, so on and so forth, where you are breaking it down. You're breaking the relationships down. So here, K equal 2, this hyper edge 1, 2, 3, 4, now you have a 1, 4, 2, 3, 2, 4, blah, blah, blah. So of course you can have the same density and different overlapness. And so you should look at more than density. Again, I feel like I'm preaching to the choir here. And then we looked at the patterns that people have found. We have references to all of these. So we looked at both static and dynamic patterns that people have shown. Again, this is not an exhaustive list. So for the static level, for example, we know that the real world hypergraphs have heavy-tailed degree distribution. They have heavy-tailed hypercoreness. They have core periphery structure. At the hyper edge level, they have heavy-tailed size distribution. So you have a lot of hyper edges that don't have as many nodes in them. And then you have few hyper edges that have lots of nodes in them. And then you have the sub-hypergraph level This is like at the subgraph level. Again, you have the heavy tail group degree distribution. And then at the hypergraph level, we know that there's a skewed singular value distribution there. And then with the dynamic networks, there's a lot of it in terms of, okay, there's going to be frequent hyper edges, right? So think about a lab. The people in the lab keep publishing papers with each other. There's temporal locality, temporal reinforcement. These are at the hyper edge level. And then the rest of it. So for example, one of the things which is interesting is that similar to graphs, this was a noted paper by Falutzos, so Christos Falutzos, John Kleinberg, and Yuri Leskovich, where, you know, you have densification of network and shrinking diameters, and we also see this in the hypergraph level. So then you can look at the generators that are out there. These generators want to generate hypergraphs that are faithful to real world hypergraphs. And so we broke it down into the ones that actually generate a full hypergraph and the ones that generate a sub-hypergraph. And so we have this table of, like, if you pick one of these, which properties of a real world network do they preserve? So do they preserve the number of nodes, the node degree distribution, the hyperedge size distribution, other information about the input hypergraph, the entire hypergraph, number of hyperparameters that they use. And so you can see which ones tick the boxes more, and also what is their big goal. So then we looked at some applications. So there's applications to algorithmic design, to machine learning, to generalized hypergraphs, and to distances. So I'm very much interested in similarities and distances, maybe because it's an ill-defined problem. So what is a meaningful distance measure? It doesn't have to be a metric, a distance function between hypergraphs. We have used hypergraphs in August. On August 12th, I'll talk about it, to speed up constraint optimization, constraint combinatorial optimization problems. But obviously in machine learning, you're looking for anomaly detection, recommendation system is where all the money is, link prediction, etc. So that was today's lecture with these two, with a side on homophily, because I think this is the audience that should work on homophily and higher order structures. I don't know if you know of other work that I didn't describe. That would be fantastic. Maybe it will be your next paper. And then on August 12th, I'll talk about these two papers and maybe two more that we'll have preprint. Thank you very much. I know I covered a lot. You can download the slides at this QR, or you can type the URL. Thank you. On time.
Any questions for Tina?
Yes.
Yeah, it was, of course, a very impressive survey.
Thank you.
A lot of experience with hypergraph. So if I present you a large hypergraph, what would be kind of the first test or measure that you would apply if I allow you to only use one measure to apply to the hypergraph?
Oh, just one, like look for just one pattern.
Yeah, what would be your favorite one?
Whether the connections are random, like how far is the connection from just it being random? Is there actual information in there?
Yeah. Okay.
Yeah.
Then of course the question is what is really the random basic non-model of random hypergraph, because there are several ones that have been proposed in the literature. What would be your favorite one?
Yeah, of the three which I presented, I like just the simplest one. Oops, sorry. No, I can't go, which was the configuration model. But it's a very good question that you're asking, because we have this other work that we're doing with students at the Network Science Institute about what is a good null model for a hypergraph if you care about information spread, right? Because it also depends on the application that you care about. But I typically go for the simplest and the computationally more efficient one. It is so, and I think that this is a good start. But that's what I would do. If there are other better null models, I'm all ears. And that's another area that the folks who are here can work on, right? And come up with new null models for different tasks, for example.
Any other questions? Okay, let's thank her.
Thank you.